Okay, why don't we go ahead and get started. So this is the sixth and final session of the LSST AGN Science Collaboration's meeting and a meeting. In this last session, we have Sebastian Hoenig from Southampton talking about AGN reverberation mapping with LSST and foremost tides. I'll remind you that WS Code of Conduct and the AGN Science Collaboration Code of Conduct apply. This will matter more during this session because the last hour of the session we're going to use for an open discussion. So we'll actually turn on microphones for everybody and allow more of an actual discussion format instead of the question and answer format that we've had before. So as with all the other sessions, it's being recorded so people that can't attend can watch it later. And again, the question and answer, at least for the first talk by Sebastian, submit at the bottom, and then we will open it up for discussion after that. Sebastian, go ahead.
Okay, so thanks for the intro. I hope everyone can hear me all right. Okay. Yes. Can you? Okay, good. All right. So yes. So thanks for giving me the chance to talk about tides and foremost a little bit. Well, first of all, I'll tell a little. Well, whoops, that wasn't intended. Sorry. Okay. So yeah, here we go. Okay. So first, I'll talk a little bit about tell you what tides actually is, what we want to do with tides. And then I'll dig into the reverberation mapping project and LSST. Specifically, I'll give you a bit of an introduction again on reverberation mapping, but you have heard already something from you, Shannon, this morning. But I just want to recap a few things in case some people didn't listen to the talk this morning. And then I'll briefly skim over the three science goals that we have, which are black hole masses, obviously, but then things that may not be that obvious, which is cosmology, and sub-parsec scale supermassive black hole binaries. And finally, I want to talk a little bit about opportunities of how to get involved, specifically for the LSST AGN Science Collaboration, but also for the community, if you want to join either that project or join the AGN Science Collaboration and contribute. All right, so first of all, an overview of TIDES. So what does TIDES actually stands for? It's the Time Domain Extragalactic Survey within the foremost projects. And we needed to come up something with tides because there's another big survey, the biggest extragalactic survey, which is WAVES, which means we had to have some maritime theme here. And tides seemed like the right abbreviation here. Tides will be run on foremost. Foremost is effectively a new instrument on an old telescope, but as the telescope is quite odd, it's kind of a completely new thing. So the telescope is the 4-meter currently infrared survey telescope on Paranal. It has a very weird optics. It's an f1 telescope, which gives you an extremely large field of view. As I told you, at the moment, there's an infrared wide field imager mounted, but this will come down next year and will be replaced by this multi-object spectrograph. There are 2 lower resolution spectrographs on it with a resolution of 4,000 to 8,000 in the optical and 1 high resolution one with 18,500. This is mostly interesting, the high resolution one, to the stellar community, even though I'll tell you later, we may actually have some use of that in extragalactic science as well. Total is 2,400 fibers, but I'll tell you later that we'll only have a fraction of those fibers for, well, each extragalactic field. The important thing is that it's really an extremely wide field survey. Each pointing covers 4.1 square degrees. So it is pretty, well, it's not perfectly matched to LSST in that sense, but we cover at least a good fraction of any LSST pointing. Yes, the sensitivity, of course, is also pretty good as it's on a very good site. It's a 4-meter telescope, which is not quite 8-meter, but still, I think at the moment, the largest spectroscopic multi-object spectrograph available, which of course makes it a prime target for LSST follow-up, etc. And this is also the reason why we started the TIDES survey, first and foremost, it was a goal to essentially harness these spectroscopic capabilities on a wide field and follow up live transients as LSST spits them out of the nightly run of their difference imaging software, etc., and essentially try to have a rapid turnover in terms of spectroscopic follow-up. So here I say 3 to 4 days, but actually the minimum time that we can achieve is probably 6 hours. So we can potentially get a spectrum 6 hours after it has been detected by LSST in good circumstances. Then of course, another interesting thing here is we can spectroscopically classify supernovae and can get out all of these type 1A supernovas that people want to use for cosmology, and build a pretty interesting, new, very populated Hubble diagram, and very pure one. And for that, we are essentially plugging into the LST's data stream. The second part is we are going to follow up of host galaxies of confirmed supernovae. Again, this is mostly for cosmology, so that we get redshifts for those supernovae, type 1A supernovae, and can put them on a Hubble diagram. And then finally, TIDES RM, the Reverberation mapping survey, where we're targeting somewhere between 700 to 1,000 AGN with the goal of determining black hole masses, making a Hubble diagram of AGN out to redshift 2.5. I'll come back to that in a second, and try to confirm some supermassive black hole binaries. I say 700 to 1,000 because it's quite a dynamic thing. We have about 25,000 fiber hours allocated. If you calculate it for a 5-year survey, you can probably get to about 700 sources. However, it is expected that some of the time lags are actually kind of recovered during the as we go during the survey, so we can switch targets and thus crank up to about 1,000 targets. Okay, so TIDES RM and LSST, how do they actually play together? I mean, again, quick recap that you all know that AGN are very variable on timescales, from intradays to weeks, months, years, and it's strongly dependent on the waveband. Of course, it's very variable in the X-rays, where it's coming essentially from a very small region around this massive black hole. If you go to longer wavelength, the variability time scale becomes longer up into the optical and infrared. And then interestingly, of course, here on the right side, we have on the lower right panel, we have a UV continuum at various wavebands where you see strong variability. And on the top right, you have the corresponding emission lines. Here, as an example, Lyman alpha and carbon 4. And you can see that they essentially mimic the same pattern as the continuum, but just with a little bit of a time lag. And this is exactly that time lag that we want to recover in AGN to use for these very science goals. Now, the plot before was relatively clean. This is marker N50, which comes from an actual reverberation mapping campaign, and I think Aaron Barth may be on the call and remember this one. So it's not as clean as you may sometimes imagine, but still you can recover lags out of this one. And then, as US said this morning already, just based on the virial theorem, you can use the RMS width of the emission line plus the time lag and a fudge factor, which has geometry and other factors in there, and get a black hole mass out of it. So that's the standard use of reverberation mapping, which we'll also, of course, do. Now, where do we want to do it? We want to do it in the deep drilling fields of LSST. And why do we want to do it there? Of course, this is simulation from an old OpSim run where you can see LSST nightly coverage. And you see that those fields that, of course, are hit most often are the deep drilling fields, which means you get pretty clean light curves in a continuum light curves anyway. We have in TIDES, in foremost, in general, we have these deep drilling fields also covered with a 7 to 14 days cadence, which means that we can combine high cadence continuum light curves with relatively high cadence spectroscopic light curves in these deep Trilling fields. Right. Now these are essentially the constraints from LSST. So we get these kind of very high light curve and well, regular coverage, hopefully even in a rolling cadence, if that should happen in the deep Trilling fields. But what are the constraints from that we have from FORMOS in general? So TIDES itself is a relatively small survey. It's one of 10 surveys, which means we have to kind of fit into the whole schedule. Unfortunately, for all that matters, supernovae are at least as restrictive or as demanding as the reverberation mapping campaigns are. So we can just piggyback on whatever they demand. So I said here that we have at least 12,000 fiber hours. Turns out we have 25,000 fiber hours, which of course gives the survey a little bit more bang. Yeah, the important thing is that per pointing, we cannot essentially get 100% of the fibers, but we usually get only 4 to 5% of the fibers, which means maybe a dozen or a few dozen depending on the current schedule. But for deep Trilling fields, that should be sufficient with to allow for these 1,000 objects over the entire lifetime. I've already talked about the goals broadly. The important thing is that our main target are objects between redshift 0.2 and 2.4. This is where we can use H-beta and magnesium-2 for black hole mass determination or determining light time lags. In principle, we can go out further to redshift 4 or beyond with carbon-4 and maybe even other lines. As you said this morning, however, in my planning for TIDES RM, I'm a bit more conservative, and this is kind of the major region and major well, selection criterion. I'll show you later, if you ignore kind of hard cutoffs in redshifts, how the redshift distribution actually looks like, and it comes out anyway, given the magnitude limit that we're having to about this. All right. Now, why do we need LSST? The important thing is, well, I said we need continuum light curves. In principle, you would say, well, we have continuum in the spectra. Why would we need that? The important thing is that if you use the continuum that you have in the spectra already, and here I show some examples of spectra where you essentially just would need to decompose it into continuum and lines. If you do that, then the problem is you buy in loads of statistical and systematic correlated errors and correlated noise in your reverberation campaign. With exactly the same cadencing and window function, which in Fourier space is an absolute nightmare and creates artificial correlations. So you may cause correlation in the whole reverberation mapping campaign that you don't want to have. So the best is to have an independent, hopefully higher cadenced support survey like LSST in that case for the reverberation, spectroscopic reverberation mapping in TIDES. All right, so black hole masses, I don't need to say a lot about this because you was quite exhaustive this morning already about this. Again, the idea is we have, we know that there's the M-sigma relation in galaxies where the stellar velocity dispersion is tightly correlated with the black hole mass. And the interesting thing is, how did it actually come to be? So people want to see how the evolution works. Now, the problem is that at the moment, what you have to do is you cannot determine dynamically the black hole masses in the early universe, at least not directly. You can do it indirectly via line width, etc. But you always have to calibrate it against local samples. Now, what you can do with reverberation mapping with TIDES here is you can actually dynamically determine these black hole masses out to, as I said, conservatively redshift 2.5, and if you invoke carbon-4 as well, maybe redshift 4, and essentially try to trace that evolution through essentially the peak of cosmic star formation and AGN activity. Yes, the important thing is that well, you are going through redshift space, which means you cannot take all of the all lines that you use at low and high redshift simultaneously. So you need to make sure that you have you can calibrate some AGN in the overlap region, which is about redshift 0.6 to 0.8 or so, where you can simultaneously have H beta and magnesium 2. And then further out, if you want to do carbon 4 at a higher redshift range. But again, you don't need to do it if you kind of limit yourself to 2.5. And why would we need limit ourselves to 2.5? Because if we just take the limiting magnitudes of our survey, this is what comes out. And we essentially drop off pretty dramatically after about redshift 2.5 to 3 anyway. So we won't get too many objects beyond that. All right, this is just distribution of H beta lags and magnesium 2 lags that we expected to get, just for information, in case anyone is interested in that. Now, cosmology. Again, this was already mentioned briefly by Yue this morning. There's the Lag-luminosity relationship, which of course you can use, which can use as a standardizable candle, meaning you turn essentially your tau into a luminosity and can, as shown in this equation here, can essentially turn that in a distance modulus together with the brightness of the object, which has been proposed in 2011 by Watson et al. And Haas et al. Here's the example of the Watson et al. Paper where they use some local AGN and essentially just show how this should work in terms of Hubble, in terms of a Hubble diagram. The important thing is that there are, of course, these caveats that you said this morning already. There may be Eddington ratio, accretion rate relation, and you have to make sure you understand how this essentially widens the correlation. There are now several studies like the Du et al. Study, Yu et al. Study, and we have a study from the Polish group, which propose ways to essentially account for this effect. And if you do that out of tides and simulate kind of the lags that we try to get, then this would be the Hubble diagram that we get out of our sample, which is actually pretty good. And the cool thing is that together with our supernova, this would be the final Hubble diagram that we get for all objects together. And you see we cover a pretty wide range with lots of objects. All right, now the final science bit is the supermassive black hole binaries. This is something which I think is, well, it's a bit experimental, but also I find pretty neat and also pretty new, as some simulations on this have only recently shown that this is actually feasible. So the important thing is that if you look at supermassive black hole binaries at distance of maybe, they're separated less than 1 parsec, maybe about 0.1 parsec typically, then they are simulations would suggest that they have both a circumnuclear disk surrounding both black holes, and then they have small accretion disks around each of the black hole, which means you have really 2 AGNs that are fed by themselves, and then you have also mass accreting inward. Here are some new radiative hydrodynamic simulations that I'm doing in my group currently on that to make some predictions. But the important thing is, this is essentially the place where this so-called final parsec problem occurs, where black hole merging supposedly stalls, or we need to find a way of how to get it, how to get the AGNs closer together. And what has been proposed recently is that if you actually have these 2 AGN with these 2 separate accretion disks and broadline regions around them on these scales, then you can actually see the binarity in the kinematic system and in the kinematic signature. So these are velocity delay maps from Wang et al. 2008 that they showed, and then in a follow-up study by Shang et al. 2020, they essentially took these velocity delay maps and ran them through some simulations of observations, and then tried to recover that. And on the right side here, you can see these are the recovered delay labs, which essentially show these signals of binarity, the signs of binarity. So this is an interesting thing. I should also say that this, of course, goes together with well, odd shapes in spectra, which means that you can actually select from spectra, or potentially even from some time signal in LSST. You can select candidates, target them specifically in foremost, and then do these well, kinematic modeling of these sources.
About 2 minutes, Seb.
Yes, okay, so I come to my essentially final bit, which is how can you get involved in the project? So again, I'll give you the little rundown of what TIDES data looks like. So it's about 25,000 optical low resolution spectra of up to 1,000 AGN. Limiting magnitude is about 21.2 magnitude here. We will be primarily looking at the standard deep fields with potential the extension to the new Euclid Deep Field South, which is currently in the debate. Nominally, we have 14 days cadence. However, the deep fields will probably be revisited every 7 days with foremost, because the waves, the big galaxy survey waves, is more demanding in terms of how many epochs in the deep fields they require to cover all of their galaxies. So that we'll probably get a pretty decent revisiting timescale of the deep fields and good cadencing. And the thing is, we are of course very short on people at the moment. So we need to still make sure our object selection is fine. It will be a dynamic, as I said in the beginning. We need people who are interested in analyzing these data, collect long-term light curves, which is of course something that we need to do currently as part of the AGN Science Collaboration anyway, precursor light curves. There's synergy with SDSD5, with US project, which we'll probably explore in the next few weeks of how we can coordinate that. And of course, there's further confirmation of these binary candidates. So we need people who actually identify candidates or bring us some of them. So there's lots and lots of work that needs to be done, or opportunities how you can help and contribute to the project. And if you're interested, please just shoot me an email and we can see where you can fit in here. I'll just leave you with a summary, which essentially just recaps what I just said. And I'm now happy to take questions. Thank you.
Great, thanks, Ed. So we've got a number of questions so far, and people can keep putting them in the Q&A while Seb addresses the first ones. So Michael Strauss asks, will TIDES pointings be coordinated with LSST? That is, will you know night by night where LSST is pointing the plan for TIDES observations?
Okay, so I mean, this mostly affects the live transients. And this is a little bit of a contentious topic in the consortium at the moment. I think officially Foremost doesn't know anything about LSST, but there is there's a big sense that as we are there near LSST, well, both in terms of space as well as we have this large area, and we'll probably observe similar parts of the sky anyway. We can try to, well, maybe not follow, but try to have a good overlap every night with LSST. And at the end, this will probably be somehow invoked. But again, this is still some discussion of how we can actually do it. We will not directly follow LSST, but we'll probably have some strategy to have decent overlap.
Great. And David Westman's here, Michael Strauss is following up saying, for what it's worth, LSST will publish its observing plans for each night. Okay. David Westman says, how do you compute the structure function to take into account the cadence variation due to daylight and bad weather?
For which part? For the reverberation mapping? Can you follow up? Because for the reverberation mapping, it's not as critical. The thing is, we are not looking at power spectral distributions. We're essentially looking at time lags. And what we are doing is I developed a forward modeling code that I'm currently testing, and I'll do getting some first science results out for the dust side, but it can also be used for BLR. And for that, this essentially mitigates any problems that you have in terms of, cadencing or uneven cadencing, etc. It's actually a feature in that sense. So I'm not too concerned about this.
Okay. Matthew Graham comments that Kelly 2020 argues that kinematic signatures are only observable with lower mass secondary AGNs. Mm-hmm. Comment on that, or?
Yeah, so the idea is that you need uneven black hole mass. Yes, I've seen the paper last week. Yeah, it's actually interesting because we may probe a different. So there are some other projects that try to find these subparsec scale supermassive black holes in the 2020s. One is actually with interferometry, but that would actually look at a different parameter space. So I'm quite mindful that here we may have completely completely different parameter space than what others usually look at. So yeah, I think it's a feature in that sense.
Okay, and Maurizio Paolillo says, since we find about 30 variable AGN in Cosmos down to 20.5, I guess for LSST you'll have 300 per DDF. So in total, a few thousand. Are these enough to beat the systematics for cosmological studies?
Yes, so the simulations would say so. At the end, you are not. So if you have the lag-luminosity relation, okay. So what I should say is that if you look at the luminosity spread that we are observing of the AGN, they are mostly mid to high luminosity Cepheids. They aren't usually QSOs, and the reason is because if you're looking at QSOs at redshift 2.5, of course the lags become very long because of the cosmological time dilation. So you are looking at probably mostly at Cepheids where you can recover time lags. This is also, if you look at kind of the magnitudes that we are getting there, this corresponds to the mid to high end of the Cepheid regime. This is also where we have the lag-luminosity relation established effectively. So if you know the lag-luminosity relation, and if you're only drawing from objects from this established lag-luminosity relationship, you can actually model what your biases would be. So you know which part of that lag-luminosity relationship or which cutout you essentially observe. So this the simulations that I showed essentially took this into account, and it seems like we can beat those systematics.
And then Yue Shen says, I'm a little worried about dynamic selection of targets. The fidelity of lag measurements improves with the duration of the light curves. You could be detecting some fake lags with short duration and remove them from the target sample in the dynamic queue. Need longer baseline to confirm these lags.
Mm-hmm. So by dynamic, what I mean in that sense of removing targets is the following. So we are in the deep fields, we have quite a number of objects that have already been monitored by OSTAs, for example. And one of the ideas is to include quite a number of these OSTAs targets, where at the moment we are having maybe even maybe we have already a lag, but it's quite it's not well established yet, or where we just need maybe 2 or 3 years more to get a really good lag out of that. So it's essentially harnessing of what's already there, using that data and just prolonging it, and then once we have the lag established, then kicking it out. It's not essentially kicking out new sources. It's taking the old ones, bringing them to an end, and then leaving them.
Okay, great. And Neil, you want to go ahead and just ask your question?
I was hoping perhaps you could say just a few more words about ways that SDSS 5 black hole mapper and TIDES RM might constructively coordinate and cooperate. They are targeting similar fields with similar science goals. SDSS RM will be on the sky first, of course.
Exactly.
So it would just be a shame to have 2 separate groups doing the same thing and everybody reinventing the wheel. And the other thing I will just warn you is certainly the experience from SDSS RM is this is a lot harder than it looks. Just getting the spectra flux calibrated to a sufficient level to do reverberation mapping with decent fidelity is a huge challenge, and took an enormous amount of work from very good people to make that happen. So what are your thoughts on these types of matters?
Okay, so
more detail.
Yeah, so with SDSS 5, so I mean, I had a very, very quick chat, when was it, last year with you already? So well, how I would envision it, but again, this is something that we actually need to discuss over the next weeks anyway, is that as you guys are on Sky first, and you cover at least the northern parts of the deep fields, you're probably not going into Elias South here, but the more northern parts of deep fields beforehand. And as your telescope, I think, is a little bit smaller, I assume that you'll mostly select from the brighter end of this AGN, of the AGN population in the deep fields. And what, of course, TIDES can do is it can take over those AGNs where no good lag had been established, but it can specifically also target those AGNs that are fainter, which of course increases our the whole sample fidelity if you take both of them together. Of course, we should have some overlap in targets to have cross-calibration between the different instruments, etc., to be able to do that. But yes, I mean, overall, my goal would be to, at the end, essentially combine the maybe 1,000 AGN from TIDES with 1,000 AGN from SDSS5 and get 2,000.
Okay. And can you remind us, when do you practically expect to have real reverberation mapping data flowing and being able to be processed and such?
So pre-COVID, it would be 2023-ish.
Okay, got it.
But there's of course now also this delay. So normally, the instrument should have be at the mountain next year with a start in 2022. But of course, we need to do kind of pre-spectroscopy for target selection, etc. So I would have thought that in early 2023 we would get the first flow of data. Yeah, and I should also say the interesting thing is that nominally TIDES runs for 5 years. But the PI already told us that we should consider that the foremost surveys actually run for 10 years. So we could essentially be on Sky much longer, much into the 2030s, effectively.
And what are your plans to achieve flux calibration of your spectra down to a couple % level?
Okay. Well, this is the challenging thing, but we fortunately in the RM in reverberation mapping, we are not the only one facing that challenge in foremost. There are also stellar people and some of the extragalactic people who want the same level of flux calibration. There are currently working groups within the foremost consortium who look at exactly that problem, and well, I hope it will be solved by then.
Right. So it's good that working groups are working on it, but yeah. What is the plan? What are the nuts and bolts of what you're going to do to make it happen?
Yes. So one of the things that there's a calibration strategy now that of course a certain number of fibers per field scattered throughout the field will be used in calibration targets. I mean, as we know, the deep fields are relatively empty of stars, but not fully empty of stars. So they will be used. And then of course we'll try to use the standard the calibration against narrow lines in the AGN. Of course, there's a problem that at the moment we don't know what how each fiber will operate and how each fiber will work and how the spectra essentially will come out there. So we have to wait for commissioning data to test all of these strategies, right? So I hope that once we get first commissioning data, I can come back with a proper answer and say, well, this is actually what we do. We have at the moment, there are just a few opportunities. We try to collect all the data to do that. But well, if you have other ideas, I'm certainly happy if you tell me them.
Great. Yeah, we should chat about that. Maybe you can join a SDSSR on Telecon sometime, and we can discuss such things further. Yes. Okay.
Okay, great. Thanks, Seb. I'm going to turn it back over to Neil in a minute here. I first want to thank all the speakers for today and for all the sessions. And then also thank Neil Brandt for putting together this very interesting and useful meeting. Neil did a lot of hard work to get this together, so thanks, Neil.
Okay.
Before we go on to the discussion session, I want to let people know, we'll maybe get a little technical. I'm hoping people will stay, but if you're not interested in staying but are interested in getting more information about the AGN Science Collaboration, I put a link to how you can apply to the AGN Science Collaboration in the Q&A.
Hey,
right.
Gordon, before we turn everybody over, maybe I can just present 1 or 2 slides very quickly just to get everybody on the same page.
Yeah, so
Okay.
so what's going to happen is, Nia will basically get us all on the same page, like you said, and then we will start basically allowing people to speak or, making them panelists so we can have an open discussion.
Great. Okay. Can you see my slides now?
Yep.
Okay, great. So these are just taken from the talk, but I just want to remind everybody. So what we'd like to do, at least for part of the next hour, is to have a productive discussion on the issue of metrics. And I want to just remind everybody of where we are in the survey strategy optimization process. So LSST has this huge multidimensional problem trying to determine the best observation strategy to get the most science out of LSST broadly. And this is being done with the survey strategy optimization process shown here. And the goal ultimately is to determine how to observe the main survey, which is most of the LSST time, as well as to spend 10 to 20% of the time on so-called mini surveys. And the mini surveys include the currently specified deep drilling fields, potential additional deep drilling fields, TOOs, studies in the galactic plane, the further observations in the north ecliptic region, the Magellanic Clouds, and so on. So there's a lot of people that want this 10 to 20% of time. Okay, so there was going to be real pressure between different groups in trying to get what they want. And if the AGN Science Collaboration has a coherent plan that is generally agreed upon, we can advocate for our interests a lot better than if we're just chaos. And so here shows a little timeline of how things played out. Back in July of 2018, a call was issued for white papers on cadence, survey strategy issues and cadence issues. And the AGN SC put in 2 white papers. They're shown here. I mentioned them the other day. One was focused on the deep drilling fields, okay? And one was focused on the issue of testing AGN selection using rolling cadences. And these include within them a bunch of metrics already. One of the main points of these white papers was to suggest metrics, and I'll define exactly what we mean by a metric in just a minute, that lets one quantify when a survey has been successful in achieving a certain science goal. Okay, the white papers were received back in November of 2018, and then the LSST Science Advisory Committee did a review of all these white papers and made a list of recommendations for next step operations simulation runs. And this was publicly available as of about a year ago, and it's well worth reading. So if you want to read the best current thinking about what the LSST surveys overall are going to be like, they're written down in this document, which summarizes a lot of the inputs from all these white papers. Now then, presently what's going on is the project is running a large number of operations simulations where they simulate the full 10 years of the LSST survey, and they do this for a bunch of different choices of parameters as specified in these white papers and then as advised from the Science Advisory Committee. And these simulations are converging, are coming along right now. Some people are working very hard and doing very good work trying to deliver all these simulations. And these will then be delivered to the so-called Survey Cadence Optimization Committee. And the members of that committee have just been named as of a few days ago, officially. And these people, we should be grateful that there's a set of people that have agreed to take on a lot of work over the next year, mostly, I think, unpaid, to help make choices, the real hard choices about what the LSST survey cadence is going to be like. And so this committee, the SCOC, is a very important committee, and we will need, as the AGN Science Collaboration, to be interfacing with this committee over the next year or so to represent our interests in AGN science. Okay, so that's what I say here. We need to interact effectively with this committee. And to do this, we need to be working through the available operations simulations. And some people in the AGN Science Collaboration are already doing this. Hopefully other people will be doing it soon. And the idea is to look through the actual operation simulations and then make assessments as to whether the planned surveys that people are talking about allow your specific desired AGN science to be achieved. Okay, and the way that's going to be done ultimately are with what are called metrics. And so before we launch into our discussion of metrics, I just want to define very clearly what a metric is. So a metric in this sense is a specific criterion that lets one evaluate the performance of a given LSST survey implementation in achieving your desired science goals, whatever they may be. And this should be ideally expressed as a heuristic tied directly to the observing strategy. In other words, we want a certain number of visits within a certain window of time with a specified set of filters. That type of thing is what you want to break it down to in terms of the level of description. And you want then a clear link between numbers of visits and within a certain window with a specified set of filters with the resulting effect on science, okay? That's the type of thing we're looking for with metrics. And many of you who attended this session probably noticed that many of the invited speakers gave a slide or two on metrics. And they very kindly, all the invited speakers actually have now, almost all the invited speakers have emailed me a bunch of metrics, and I compiled these and shared them with all the members of the AGN Science Collaboration. Sorry, I wasn't able to share them with everybody on this particular telecon or Zoom meeting because I didn't know who everybody was. But if you want to see the types of things the AGN Science Collaboration is thinking of in terms of metrics, you can email me and I'll be happy to share the collected metrics that we have so far with you. So the idea now is to discuss some of these metrics. And if people, especially I would say, if you feel that your science is almost surely going to be fine, given the currently planned surveys, then probably there was a need to say a whole lot. But if you're really, especially we want to hear about people who are concerned about something, where people are thinking that the current LSST surveys are not going to let you do the AGN science that you want to achieve. That would be very helpful to hear about. And so with that, I will stop. And I will stop sharing my screen, I guess, for now. And we can start letting everybody be capable to speak. Does that sound good, Gordon? No, I'm not hearing everyone.
Yeah, so we can start turning on.
Okay, great.
For everybody.
Okay, great. You just click the allow to talk. Is that what we're doing?
Yeah.
Okay, I'm just going to do that. Start doing that myself here.
You have to do this one by one, huh?
Yeah.
Yeah, we're here furiously clicking away, but I think people are now. I think that's everybody. So I think everybody now, if you unmute yourself, if you wish to express your thoughts or opinions, by all means, feel free to do that now. I mean, let's try just not to talk over each other and such as best we reasonably can.
And before we do that, I'll remind everybody we're still recording and intend to record the whole session.
Yeah, that'll be helpful for future reference, because especially if people are concerned about something, you want to be able to go back and consider it carefully.
So Neil, how do you want to start? You made a list of metrics.
Yeah, I mean, I can share my screen and just start putting up these metrics and we can start talking about them.
I think that's a good idea, actually.
Is that a good idea? Okay, fine. I will just share my screen then. And this may be just a little messy because I gotta see how am I gonna do this. I'm just gonna share my overall desktop. Hopefully you can see that there.
Yep.
Okay, so I'll just start tossing out. I'll just start going through these. Here is a metric. Can everyone see this? I hope.
No, much too small. Please.
Oh, I don't know how to make that bigger.
You would.
Let's see here.
I
think I can do maybe I can do this.
Plus or something.
Yeah.
Oh, can I do that?
Command plus,
okay.
Absolutely.
Okay.
There we go. Now those of us with age eyes can actually read
it.
Yes.
Is that better? Okay,
yes,
good.
Thank
I'll
you.
make it even bigger. Okay, so here is one from Roberto Asap, and I'm just going through alphabetically here. And so Roberto, who is, again, leading a lot of the PhotoZ efforts right now, put forward a metric where basically he believes that to get the best possible photometric redshifts, you essentially want uniform depth across all the bands, and that certainly includes being deep as possible in the U band. And that's the same basic thing that we arrived at in our considerations of the deep drilling fields that we wrote in the deep drilling field Cadence white paper. But I'd like inputs from people. If anyone thinks that we're missing something there, we'd like to hear about that.
So if I can comment, first of all, I believe Roberto is making this comment in the context of the wide survey, the main survey, not the deep drilling fields, or perhaps both.
Are you on, Roberto? I hope he's on. Okay,
yeah,
go ahead,
I'm on.
Roberto.
Yeah, you're right. This is I'm thinking primarily of the wide field survey.
Fine. One of the things that we want to keep in the back of our mind is that we want to do science throughout the 10 years of LSST, not just when the whole survey is over in 2032 or whatever it may be. So one of the things that we want to keep in the back of our minds is the extent to which we want to, whether this uniform depth is important after the first year, for example, or what we would do with the inevitably patchy data that we might have after the first year, and whether that's really going to stymie us. And one can imagine metrics that ask these questions directly of an operation simulation, which is, how much uniformity, for example, do we have over the first year? And it's worth thinking about the extent to which we really care. So just throw that out.
Do you remember, Michael, from your looking at the OpSim run so far, the level of uniformity for wide, fast, deep in general?
Well, I mean, one of the things that has certainly been a subject of discussion quite a lot in the SAC and elsewhere has been whether one wants to put that in as a specific requirement. If you don't require it, it will not happen. That is, if you don't put some sort of extra, if you don't put a cost against, if you don't sort of build it in, it will be somewhat haphazard. And in particular, I said the first year I was being a little bit sloppy. In practice, it takes about 1.5 years to sort of close the sky at the beginning of the survey. And so, survey strategy has sort of recognized that, and there has been some attempt in some of the simulations to try to enforce a uniformity. But again, it's worth having metrics that can allow us to quantify that.
Okay. Does anybody else out there have any inputs? And you don't have to be a member of the AGN Science Collaboration. If you have experience with photometric redshifts and you think that the AGN Science Collaboration is doing it all wrong, please feel free to speak up now and tell us, because we're happy to correct our ways if something is incorrect. Okay, seems like that one is okay. Do you have anything else you want to add on these matters, Roberto?
No, nothing for now.
Fine, okay.
Hi, Neil, this is Pat Hall.
Hey, Pat, yeah.
I realized I did just have a question. When you say uniform depth in all bands, do you mean that we want as close as possible U-band uniform depth across the sky, and as close as possible G-band uniform depth across the sky? Or are we talking that you want, uniform depth in all bands, U, G, R, I, Z, Y, which would mean, I think, sacrificing some integration time on the redder bands in favor of integration time in the U band? Yeah,
well, when we thought about it in terms of deep drilling fields, I'll let Roberto speak for his case, but certainly in terms of the deep drilling fields, we wanted pretty uniform depth across the bands, U, G, R, I, Z, Y. Now, clearly, that is practically just probably not possible to achieve fully in the U band and in the Y band, but one can strive for that to the greatest extent possible. So that's what we were aiming for. Is that answering your question, Pat?
Yes.
Okay, and Roberto, you were thinking a similar thing, right? Okay, uniform depth across the bands. I mean, clearly we wanted to cross the sky as well, but yeah. Yeah,
pretty much. And the reason I wrote it as deep as possible on U is with the kind of understanding that it's going to be hard to get to the same depth in U as in the other bands, but we shouldn't forget to do that band as well, or to go as deep as we can. Yeah.
In fact, I remember, and Gordon will probably remember that when he was finishing one of his white papers, I started adding a bunch of text to one of his white papers saying you got to add a bunch of stuff about having great U-band across the sky. And you said that really did. Yeah, go ahead.
Yeah. I was going to say it's probably worth reminding everybody why U-band is challenging in operationally, because there are 6 LSST filters, but only 5 filter slots. So the U-band has to be, and the U-band only really makes sense to observe at the dark of the moon. So the plan was that, as it were, the U-band and the Y-band get switched out roughly on a monthly basis, and it's easy to get into a mode of, and this will come up later, let's just get the U-band done with, and then we don't have to worry about it again. And so some versions of the simulations have had, lots of U-band fairly early on in the survey, and then sort of never gets touched again. And we can have a discussion whether that's a good thing or a bad thing from the AGN point of view.
Okay.
So a related question, will there be a point where we want to add some numbers to a metric like this and saying, for example, keep U-band within half a magnitude of G-band depth or something like that?
Yeah, I mean, you basically, the way a metric gets written is a number gets spit out, which is for any given operation simulations run, you get an estimate of, sort of what the variation of the depth would be. And then you can decide after the fact whether you want to put thresholds and say, this is completely unacceptable. This would be a pain in the neck, but we're willing to live with it. And this would be ideal. Those are the kind of things that you want to do. So it's a distinction between the rules for any given opsim run and characterizing an opsim run after it's happened. Does that make sense?
Yep. Okay. Are we good on this one? Any other inputs on this one? If not, I can move to the next one.
Go for it.
Okay, so the next one is mine. Oh, go ahead.
One thing just to add, if you have any other inputs, just feel free to send me an email or contact me any other way.
Yeah, absolutely. Yep.
People think.
Yep. Okay, I'll put up the next one, and this is essentially taken directly from that Cadence white paper with this archive link. Okay, if you're interested. And so this was the white paper on the deep drilling fields, and the metrics that we put forward there, specifically relevant to the deep drilling field. And I'm not going to read all this stuff. I'll just paraphrase it. One of them is essentially that we want to make sure the deep drilling fields are sited correctly in terms of RA and DEC so that they cover the prime multi-wavelength data. And so we specified that in the white paper, and we think we made good choices there. But by all means, if you go and review this white paper and you think somehow we're pointing in the wrong place, please let us know, and we'll be happy to consider your inputs. The second one is that we want the deep drilling fields to be observed at least every 2 nights across GRI, ZY. And as we just talked about, U-band is more challenging because of the fact it's not always going to be in the filter wheel. Okay, in as regular a manner as possible. Clearly, weather will interrupt from time to time, but that's what we're striving for. This multiple band coverage is especially required for things like photometric redshift of AGN accretion disks and general AGN variability characterization and supermassive black hole transient characterization. Those types of things is what we're aiming for. And that's a pretty dense sampling. Just to give you a comparison point, the Dark Energy Science Collaboration, which is the largest and I believe probably the most influential science collaboration in LSST, is requesting, I think, every 3 nights cadence. And the reason we went for every 2 nights is, in fact, that there were some simulations done of accretion disk reverberation mapping that indicated that if you go much longer than 2 nights, you really take a hit on deriving reliable lags. And so that's why we did that. Now, one thing we didn't do, but which I think Paulo Coppi raised during his talk, is this issue of observing all of these bands in rapid sequence. In other words, making sure we hit GRIZY within a relatively short time of each other. And there's many ways to think about this. Right now, we actually went and looked at the operation simulations, and they generally are doing that. Qing Ling, I believe, looked at this, and I think generally these are being hit within about an hour of each other, usually, okay, in the simulation. Usually that's getting done in pretty rapid sequence. But I think Yue mentioned, and he may wish to comment on this, that, in fact, it may not be so advantageous to have all these bands hit in very rapid succession. You may want to spread them out because tools like CREAM, which is the Keith Horn's advanced statistical methodology for doing this type of accretion just reverberation mapping, actually can deal with the things not being in rapid sequence. So that's another possible thing. So maybe I'll pause here. Does anybody have any inputs on that one? In terms of every 2 nights, and in terms of hitting all these bands either in pretty rapid succession, or alternatively, you may prefer that these are actually spread out a little more broadly than just within a single hour. What are people's thinking there? Yue, I believe you had something to say on this matter in your talk, right?
Yes.
Go ahead. Why don't you repeat what you said?
Yeah, so in terms of the accretion disk reverberation mapping, the transfer function is pretty broad if you consider from shorter wavelengths to longer wavelengths.
Yeah.
So having those different bands sort of shifted by a little bit, say it can straddle 2 nights instead of all packed up in a single night with rapid sequence, actually helps constrain the transfer function and also the disk models in fitting those multi-band light curves in the public code like CRANE. You don't want to stretch them too broadly, say every more than a few days. But I think if you take G band tonight, and it will actually be helpful if you take the longest band, say shifted by a day or 2, and with the intermediate bands in between. The G band and Z band.
Okay. And are you going to present the technical details justifying that in that Starkey et al. Paper?
Yeah, we'll certainly make a point on this. I think we already made a point there in the draft. I think that we should do the trick. We didn't perform a very sophisticated simulation of that. Oh, I should also mention that it also helps because now you stretch those multi-bands from 1 night to maybe 2 or 3 nights. You actually effectively increase your effective cadence. So if your main science goal is actually to cross-correlate those optical light curves with much longer delays in the dust torus, then this actually helps a lot because now instead of only 1 point, you actually have 3 points.
Right. Okay. Yeah, well, laying that out as specifically as possible in that Starkey paper will be very helpful. Yeah.
So let me remind you, there are two related exercises that we're thinking about. One is sort of the instructions to the operation simulator of how to do things. So if we say that we want to have the different bands in the deep field on successive nights as opposed to the same night, those would be instructions that we would, or merit functions, sort of cost functions that we would give as rules to the operation simulator trying to time the observations. Then but what we're looking at is, given an operation simulation, how well it meets any science goal. We're sort of asking the question, how well will any given realization actually do the science that we want? And that's what the metrics really are about. So one is instructions to the operation simulations, the other is analysis of the output of operation simulations. And so we want to make sure to keep that distinction.
Yeah. Okay. And I remember, Paulo, you had some thinking about this issue as well in terms of rapidly going across the bands. Do you have any inputs there again now?
No, except that if you have a model for how the band should vary, like if you have an accretion disk template, then spreading things out can indeed be helpful. But if you have no idea what's going on, I've usually found it ends up hurting you because you can't predict what's going on and you break causality chains and stuff, and you're sort of guessing this is what happens if you want to put things together. So the safest thing is to have truly simultaneous measurements if possible. That may not be possible. I think what I said in my comment was you can look at structure functions and ask how long does it take the source to change its typical luminosity. And AGN, for the most part, although there may be exceptions, don't do a lot on hour timescales. And even maybe a few day timescales, if you're at the 10% level, is probably okay. if you go out several months, I've seen cases of 0.3 magnitudes changes. So that potentially could mean your colors, apparent colors, if you compare G, for example, and R 3 months later, may be off by 0.3 or 0.4 magnitudes. That could happen, and that could mess things up. So ours, I think, is perfectly fine for almost everything except blazars and stuff like that. And stretching stuff out over several days, possibly for deep drilling fields, could be problematic. It could help specific models, but in general, I would find it slightly dangerous. So with other groups, we talked about like detecting outbursts and stuff like that, not having simultaneous like G and R, so you can tell if something is blue when it brightens, is a big problem. So a general comment that I think a lot of people have is being able to tell if something is red or blue with very little lag is a useful thing for LSST to do, although I was told that's not that easy, but it's
well,
good.
yeah. So again, at least right now in the operation simulations that we've looked at, and by that I mean Qing Ling, and I believe she's on and can comment further because she actually did the checking. But it looked to us like you were hitting GRIZY within about an hour. Is that correct, Qing Ling?
Yes, actually within half an hour, but I only look at the OpSims led by our science collaboration, which is the 2 version of AGN deep drilling field. And these color variations, the cadence between colors may vary in other OpSims proposed by like different groups. So it's worth writing it in a form of matrix and apply it to all the current simulations and check.
Yeah, okay. So I don't know how we converge here. I mean, do you have any follow-up, UA, to what Paulo said, or can you guys converge at some level on something that would at least be a good approach?
I guess I could ask David or who want to simulate the 2 cases where you have all the 5 bands taken within half an hour, or you have those 5 bands stretched over, say, 2 nights, and see how much better you get for the accretion disk model constraints. But I certainly agree with all those assumptions and complications built into the models, accretion disk model that we're using. I'll just say that if you want simultaneous color variability, then you definitely want to observe those bands as closely as possible in time. But if you want to maximize the information in the delayed variability, in particular in measuring the crossband lags, then making them slightly offset from each other, but not too much, only still within half a night or 1 night, will gain you some advantage.
Okay.
Benefits.
Okay. Well, maybe when you've had a chance to do that, you could pass it by Paulo. Like, he's the other one who seems to be having thoughts on this, and include me, and maybe we could come to some level of convergence. That could be helpful.
Sounds good. Yeah.
Okay, great. Okay, here,
Can
I'll
I
go
ask
to the
a
next
question?
one. Sure, go ahead, of course.
I was wondering, so how does the U-band fit in this scenario, since it cannot follow the cadence of the rest, and it will affect, for instance, the selection by color at that point if it's taken several months later?
Well, that's a good question. So we don't, to my knowledge, it's not entirely clear what will be happening with the U-band. I think Michael said correctly that you're going to want to be doing the U-band in dark sky. And so whenever you have dark available sky and the weather is cooperative, you're going to have U-band in there, and you're going to hit the U-band pretty hard. But having any kind of uniform cadence on the U-band, my guess, at least in general, is going to be very difficult. You're going to get the U-band probably clumped. I mean, Michael, you can correct me if you think this is wrong, but my guess is you're going to have the U-band pretty heavily clumped in dark sky times about once a month.
That is correct. And again, one question that it would be interesting to get the opinion of people here is whether whether we're happy with or okay with as it were, those clumps around the dark of the moon to only happen some months and maybe not all months. Is that something we're okay with? Is that something we care strongly about one way or another? Operationally, it's easier if one has to do fewer switches of the U-band filter in and out.
Well, I mean, speaking for general AGN folks, we thought that was fine when we, at least when we were writing this white paper. Although I remember that the tidal disruption folks, Sube Gazari, for example, was quite unhappy with the U-band being clumped in that way. She wanted even more better time resolution on the U-band because apparently it's very important for separating out the tidal disruption events.
But I was also wondering if Gordon's, from Gordon talk when he was advocating the use of simultaneous color and variability for selection, if the change that you have from one month to another could significantly affect this selection. I don't think we have simulated that.
But Neil, the Quingling actually did the check, right? So for one of the upsim simulations of the time gap between the U-band and G-band, for example, the average is about 5 to 10 days, right?
I don't remember. Quingling, is that correct? I don't remember what you found on the U-band.
Yes, but that's for our upsim strategy.
Yeah, right. Yeah, so so that's if we get what we want, that's how it would be. But clearly the Dark Energy Science Collaboration will have their own opinion on how things should be. And so there will be something happening. And that's why interfacing with this survey cadence optimization committee is so critical, because if we have to be representing our interests or we're going to get nothing. We'll get steamrolled.
So my comment was more just along the lines of, I think we had all been assuming, at least in the wide fast deep, that you wouldn't get simultaneous colors, but the current baseline does have that built in, and so if that's something that's important to us, then we should make that known.
Okay, here, I'm going to scroll down and just because I know we have limited time here, so I'm just going to go through these other two very quickly. So another thing that this is the same thing we just talked about, that we want pretty uniform depth across the LSST filter. So we're saying the same thing that Roberto said, but for the deep drilling fields, essentially. And this is the pattern we suggested doing to get that. But then number four was important. And I'm sure here the reverberation mapping folks will have things to say. I mean, we requested, and this is something where fortunately both the Dark Energy Science Collaboration folks and the AGN Science Collaboration folks agreed. We requested the longest observing seasons possible, okay? Because, for example, this increases the chances of robust reverberation mapping, lag detections, allows access to longer lags corresponding to higher black hole masses, and so on, and aids searches for supermassive black hole binaries. So we asked for the longest observing seasons possible, and the supernova folks and the Dark Energy Science Collaboration very much wanted that as well for similar reasons. They don't want to get their supernovae cut off, and they want high efficiency on the supernova studies, and that corresponds to long seasons. Now, I will comment there that there's a real cost to this choice. This choice does not come without a cost. The cost, of course, is that if you really want those long observing seasons, you're going to be observing often at fairly high air masses, which means that the deep drilling fields are not being optimized for depth. They're being optimized for time domain. And, certainly all the inputs I was getting when I was writing this white paper were suggesting that that's what everybody wanted. They wanted the time domain aspects emphasized and not so much pushing for the ultimate in depth. But we may get some funny glances from people, when we go around calling these things deep drilling fields, and then it's so obvious that we actually didn't optimize them for depth. And so any inputs there? I mean, I'd be interested to know. I mean, I certainly think that all the time domain people want the longest observing seasons possible, but I'd like any inputs there.
And I certainly think that is true, but what we have to realize is that anybody looking to plan survey strategy is going to try to observe at the meridian whenever they can, unless you tell them otherwise, right? So it may be that we need a metric that is more than the longest observing season possible, but rather, is something more quantifiable.
Right.
Yeah, in fact, the OPSIM does have an explicit rule, at least for the wide, fast, deep, the main survey, to as you said, minimize the air mass, and there's a nominal cutoff at an air mass of 1.4. It's a somewhat arbitrary number. But I think it's a pretty hard cutoff that unless you explicitly tell it that you're allowed to go to higher air mass, it will never schedule at higher air mass.
Yeah,
and so I know Gordon has thought about that in the context of wanting to observe at high enough air mass that you have some astrometric offset to actually go measure DCR.
Yeah, and so we explicitly, as I highlight here, we told them they could go up to air masses of 2. And Klingling, I believe that as you say, Gordon, I believe we were successful in at least in the AGN simulation in overriding that nominal default approach, Michael, that you mentioned. Klingling, is that correct? We did get quite long seasons, right? More so for some fields than others. Is that correct?
Yes, in average, 6 months to 8 months.
Yes.
So, I mean, I guess the question is, let's say if you didn't override it, you would get a 5-month season, right? You know, is it sufficient to have one epoch, you know, 3 weeks earlier and one epoch, you know, 3 weeks later to extend you 6 weeks, or is that, you know, useless and you really want the observations spread out more evenly in time?
Why? So for spectroscopic reverberation mapping support, I think you don't want that. You want kind of, well, a relatively good cadence. Well, you probably won't need every filter at a very high cadence, but you want to have, in this extra month, kind of going from 5 to 6 months, certainly a certain number of maybe, I don't know, half a dozen to a dozen observations.
Right, so you can't just say the longest observing season possible because, you know, adding, you know, one observation extends your observing season by that amount of time.
Right. Yeah. What we implicitly meant here in words is we want the longest observing season with this every 2 days, every 2 nights thing being maintained during that whole long observing season. That's what we were after. Yeah, but I agree. You have to write that in code very carefully. Okay.
And
go ahead.
Neil, if I can just say that
sure.
that raised the point that for Gordon's, you know, chromatic aberration redshift determination, you do need more than one filter, but for reverberation mapping, probably okay with just R band. So,
well, people of course do have interest in doing the accretion disk reverberation mapping as well.
True.
Yeah.
That's a good point.
All right. Okay. Yeah.
And these would still be deep drilling fields. They just wouldn't be, you know, the deepest drilling fields.
Yeah, they're not optimized for depth. That's for sure. Yes. And but I mean, somewhat surprisingly to me, the Dark Energy Science Collaboration was totally on board with this kind of an approach. There, it seemed like the supernova folks were in the driver's seat, and I have, to my great surprise, I have not yet, and maybe Michael can correct me if he's heard somebody. I have not heard anybody screaming and yelling about how the deep drilling fields aren't being pushed super duper deep.
No, I don't. What I have not seen are specific science goals that want super duper deep. I mean, you can invent such things. You know, let's go find out what the faintest galaxies out there are doing. But people have not, to my knowledge, not expressed specific science goals that say we must get to 28.5 and not 28.3, as it were.
Yeah, I mean, I guess, you know, someone like Xiaoyi, someone who wants to look for AGNs down at very low luminosities, out at very high redshifts, they might care.
Yeah, but how are you going to confirm such an object, right?
Yeah, because they're going to look like galaxies. Yeah.
Yeah, I mean, if at any redshift, something at 28 point whatever it may be, is going to be dominated by a host galaxy, even if it's a nominally type 1 object.
Yeah. So very tough.
So yeah, I haven't heard those specific science cases.
But if anybody is out there right now among the 39 participants we have online, and they think we're doing a terrible thing by not going super duper deep, I'd like to hear about it.
Neil, do you have a sense of what kind of difference we're talking about?
Yeah.
You know, at the end of 10 years, are we talking about 1/10 of a magnitude or half a magnitude?
No, it's like half a mag. I mean, that's Klingling may remember better than me, but this was the source of all of those emails back where I mean, when the first simulations came out, I was really quite surprised because I had not properly appreciated the level of a hit you take due to those high air masses, but it's substantial. It was like half a meg, and clearly it's band dependent. I think it's less bad in the red bands and considerably worse in the bluer bands. Is that correct, Qingling?
Yes, it could vary between 0.5 meg and in some cases even approaching 1 meg.
Yeah,
really 1 meg. That is a lot.
Yeah, it's substantial. I mean, you're taking a real hit, and people need to be aware of that. I mean, I was surprised when the SIMS came out, even though if I had properly read Jelko's paper, I would not have been, because it is directly implied in the full equations in his paper. But you know, one has limited time, and things pass by you. Yeah. Okay, so that's those. Yes, go ahead.
Can I, one quick comment is, we require the longest observing seasons possible. If this is only a requirement for the spectroscopic IM follow-up, then I would like to echo Pat's comment that we can do less bands than the forced filter setter. And you mentioned disk reverberation mapping, but that doesn't require the longest observing season.
Exactly. Yeah, this was my same thinking. Exactly. Is you could conceivably just have really dense sampling for 5 months, because as you say, the lags for the disk reverberation mapping are pretty short. What you really want there is super dense, maybe even daily, and then you could compromise out on the ends just to make sure that you get the longest seasons for the spectroscopic reverberation mappers. That may be a better approach. Yeah. To do it that way. You know, I mean, just pound the heck out of it. You know, when the air mass is very low, and do the reverberation, disk reverberation mapping really well for a short time, and then just say, okay, we're only going to go for 4 months of that, and then the rest of it we'll do it looser. And you know, again, maybe 2 years ago when I was writing this, if I had been smarter, I would have said that. But I did my best to compromise a lot of different inputs coming in at once. But yeah, that may be a better approach. And so we should definitely look into that. Okay, now I'm going to move on to the next one. And I see time is ticking. So let me say this. If you have something to say, I mean, if you are concerned about something of the cadences, please speak up now, and I'll put yours up, because I want to hit the high priority cases where people are concerned about something. Because I think going through alphabetically, we're going to run out of time. So does anybody want theirs put up? Because I'll be happy just to put it up right now.
I don't have one, but I had a quick comment on the U-band discussion.
Yes.
The you know, the TeV community kind of deals with that. You know, that sun, moon can't be in the sky, but they can observe before midnight on waning moon, after midnight on waxing moon, and you can throw a few things in so that you're not observing it just once a month. And then the other consideration, though, you also mentioned, I know the Chandra Observatory and probably other, like, they don't want to switch their spectrometer more than they absolutely have to. You know, they do a whole bunch of one kind of observation and then do a whole bunch of the other kind of observation. So I certainly understand that constraint as well.
Mm-hmm. Yes. Yes. Yeah. Okay. Yes. That's what, these are the types of things we struggle with as well. Yes. Okay. So does anybody want theirs put up here? Is anybody unhappy and want theirs high prioritized? If not, I'll just go to this one. I'll go to Paulo's next alphabetically. So Paulo, perhaps you can guide us through this one because it's rather complicated.
Right. Maybe Gordon can do it. We just had to talk about it. It's
okay,
basically
good.
The same.
Why don't you guys go through this one? Yeah.
Gordon, do you want to?
Is it big enough for everybody to see? Can you all see this?
Yeah.
Yes, we can.
Actually,
okay, good.
Why don't I just share my screen?
Yeah.
Okay. You want me to stop sharing mine? I'll stop sharing mine. Go ahead.
And I'm going to put Paulo's figure.
Sorry, I'm going to interrupt and say that I'm going to leave because I have to host the next plenary talk, but I urge you all to come to Christy Tremonti's plenary at 4:30.
Great. Yep, we'll be there. Thanks.
Thanks, Michael. Okay, so basically, this is the number of pairs of observations as a function of time in log here, right? And I think both Paolo and Weizhang and I are interested in the same kind of thing here, which is basically that you know, to measure the structure function, or basically just the parameters of light curves well, and Paolo Sanchez talked about this as well. You know, you want good sampling at, you know, multiple different time scales. Paolo describes it here as 3-day, 30-day, you know, 100 days. The metric that Weizhang and I came up with basically is, you know, comparing how uniform your pairs of observations are, you know, compared to something uniform. And so we basically need a metric that quantifies this. And I think what we're doing right now doesn't particularly make sense. But you know, the rough idea here is that you would kind of want the histogram to be sort of as flat as possible. You can't really do anything here at the half-day time scale, obviously, but pretty much everywhere else you can fill things in. And so we had a little side conversation, and we'll keep that going. But you know, if anybody has thoughts on you know, good metrics that basically boil down to sort of one number that say, you know, how well you'll capture things on short, medium, and long time scales, we're definitely interested in feedback on that.
So I asked a question during exam talk, and I was wondering, because in my experience working usually in real space, you want a more regular sampling to reduce the uncertainty. So I was wondering, of course, the log spacing would give you a better handling on all time scales. But I was wondering if you pay a price in the dispersion, in the sense the uncertainty, especially maybe at small time scale, which become less sampled, could take a hit. And so if there is a way to characterize also the uncertainty, because maybe if you sample a particular time scale just few times, of course, with the stochastic behavior, the uncertainty on the structure function itself is not just, you know, due to the errors, that's stochastic variability. You need a lot of sampling to constrain that. So I was wondering if that comes out of the simulation, that we can say, you know, with this pattern we get, yeah, this uniform coverage, but also these uncertainties on specific time scales.
Paolo, you want to comment on that?
Sure, yeah, that's where the idea of number of pairs come in, because if you, for example, compute a structure function, or what's the mean RMS variability on a certain time scale, you take the number of samples you got on that time scale and you end up dividing by square root of n eventually. So it goes with the number of pairs that you have there. So one requirement could be that we simply require more than 20 pairs everywhere, which would give you 20% accuracy. So that's why I think the number of pairs is a useful measure. So if your cadence doesn't generate more than 3 pairs separated by 2 hours, you're never going to learn about 2-hour variability because of what you said. You have to sample the stochastic process. So the number of pairs is an indication of how well you've sampled something. And the photometric errors also go into that, measurement errors. And so you could say, if I want to sample short, medium, and long time scales, I have to exceed 10 on this plot everywhere as a minimum. And if I don't, I have no chance, or 100. It's up to you to decide that. We were arguing what's the right number and what specific range of time scales should we do it at. But that's the rationale for plotting number of pairs, of time pairs.
And let me give some context there, right? So the issue is, you know, uniform distribution doesn't give you very many small timescale separations, right? A rolling cadence, you know, actually is really beneficial in this sense, because it gives you pairs at short timescales at the expense of pairs of long timescales. But you already have plenty of pairs at long timescales. However, an extreme rolling cadence, where, for example, if you clumped, you know, most of 200 epochs of data in 1 year, and then basically never came back to that field, you know, for 9 more years, would be devastating for AGNs, right? So we need some sort of metric that you know, captures the extent to which a mild rolling cadence is good, but an extreme rolling cadence is terrible.
I agree.
Yeah, go ahead.
Yeah, so if I may make a suggestion here, which you probably already thought about the criteria is that you probably want to get the same fractional uncertainty at each log bin of time. And the uncertainty is basically the photometric uncertainty divided by square root of n. But you do have information on the structure function amplitude as a function of time. So that could potentially give you some idea what shape of that curve you're plotting here would give you a uniform fractional uncertainty across all those log time bins.
Yep.
Yeah, and I guess the question that it comes in there is, you know, how and to what extent might we want to combine the bins to achieve that?
Well, if I just look at this bin here, this is the number of pairs. So, and if I just assume that the uncertainty of this structure function measurement at in a particular log T bin is basically the photometric uncertainty divided by square root of n. And I also know the structure function from my theoretical or whatever empirical measured one, what would be the amplitude of that structure function at say 1,000 seconds versus 10 to the 7 seconds. And then I just scale my number of pairs here to try to match the same fractional uncertainty to give you a sort of uniform measurement of data points in the structure function space.
Does that
make sense?
Yeah, he's saying fractional uncertainty, right? So if the structure function is really small, then we need to get really precise measurements to say anything about it.
Correct.
Right. Wait, John, did you follow that?
Yeah.
Okay. Okay, that's all I have to say about this one, really.
Yep,
but sorry, I didn't get, Paul, you say fractional uncertainty?
Yeah, I guess that's what was saying. Like, let's say the structure function AGN has very low amplitude at 1,000 seconds, but we really want to measure it for some reason. Then we're going to have to get really precise measurements to see anything at all. So then we need a lot of pairs.
Exactly. You just square root of n, so you have to have a lot of n to eliminate this errors.
Yep.
The complication is
I get that point. I think another thing worth mentioning is if we do fitting, I don't know if they're gonna be the same story. You know, if you do empirical structure function, you do care about the number of pairs because you're gonna do empirical measurements of the structure function. But if we do fitting, we're gonna derive that structure function from the best fit parameters. That is an uncertainty in how we should think about this.
The other thing you want to be careful about at those really short time scales is that's where you're dominated by the systematic noise component if you're trying to recover the structure function. So you have to have a really good estimate of what the systematic noise is within your photometric measurements.
Yes.
Yeah.
Which will again be dependent probably on the number of pairs that you've got going in.
Yeah, so if we have an estimate of the noise floor, basically ignore time scales shorter than that. Okay.
Yeah.
I mean, that's right, is what you're suggesting.
Yeah, or you can recover it, but it tends to be, you know, it tends to be 5 days or less is when you hit systematic noise for a lot of the surveys that have already been done because of the accuracy in the photometry.
Yeah, and I think what we'll want is to push hard on something like 2 to 3 days and give up on things much shorter than that.
But what I can tell you is even something like ZTF, even though we're doing a 2 or 3 day cadence, the structure function has no information shorter than 5 days because of what our systematic noise level currently is.
Okay.
This is more or less what we were finding with VST as well. It's very hard to get below that.
Yeah.
Is that just a function of the photometric noise? So that if you had enough AGN, no, you're still limited by the fundamental noise. Yeah, I see.
The way to improve it is to improve your photometric accuracy. So if you do differential corrections or relative corrections against the super master catalog or something, you can go further. And that's what Kaplan did with PTF in his 2018 paper.
So I have one question. So Gordon, are you really trying to improve this, the the number of pairs per, as a function of the time? Or is it just looks like that the information itself is like the noise map, some sort of, right? So eventually you want to use that noise to actually characterize your noise in the structure function, right?
I mean, let me tell you what I'm really trying to do, which is play defense, as I'm worried that the supernova group is going to come up with a proposal for an extreme rolling cadence. And if we don't have a metric and some plots to show how bad that's going to be for us, then we're going to get steamrolled.
Mm. Yeah, I agree with that sentiment.
Yep.
Okay, so I think we're running short on time in order to be able to go through more cadences. There is one other thing I'd like to raise, but does anybody, aside from all of the discussions we've just had on survey optimization and so on, perhaps we should plan to discuss some of these other cadence inputs that we got from the invited speakers at the various telecons of the science collaboration coming up. Does that sound good, Gordon? We usually have an extra 10 minutes or so on a lot of these telecons, and we can just go through these one at a time over the next month or two.
Yeah, we can definitely do that. One thing I'll advertise is that discussions about DCR are happening on Slack channel DM DCR. So if anybody's interested in that, they can follow it there.
Okay, fine. So I guess we'll just proceed that way. Does anybody have anything else they urgently want to raise? If not, I just want to talk about possible future meetings of this type. Okay, well, I'll just put up my slides then if no one has anything. So hopefully you can see these. So I mentioned this in my talk again, but it seemed to me that this meeting, while it wasn't perfect, did allow, a pretty decent meeting. And so there's a number of ways one could envision future meetings. You could have another Zoom meeting like this. The advantage being that it's very economical, which is good given that we have no funding. The downside, of course, is you don't get a lot of the interactions. I had hoped that this meeting in person in Madison would allow us to go out to lunch each day and dinner each day and have lots of additional discussions, and clearly that just couldn't happen. But so there's ups and downs, but we could certainly consider having another one of these next summer, either working with the AAS or on our own. And so it seemed, I felt that the number of talks per day was about right. I felt 6 talks per day was pretty good. And keeping the talks pretty substantial with time for discussion was helpful. I felt that, any more than 6 talks, you'd start to go into saturation mode where all the talks start to blur together and you can't remember who said what, and you start reading your email a lot and stuff like that. So were people happy in general with the number of talks each day? And does anybody have any thoughts about whether we should try to have another one of these next summer?
So in particular, I think it worked actually quite well. If we do this again, I think one thing that could work well is also have some discussion time perhaps on the first day as well.
Yeah, that would be good. Yeah, I agree. Yep. Yeah, again, this whole thing, when I designed it, of course, I designed it so each day we were going to have a lunch and maybe a dinner. And so there'd be lots and lots of time for that kind of discussion. But it just wasn't, with this switch to Zoom and everything, it just wasn't possible. But yeah, I certainly would like to do that. I agree.
You could imagine that next summer, even if we're able to have meetings in person, AAS might be willing to, support virtual meetings like this.
Yeah, maybe.
In which case, we might be constrained to have a similar sort of format. But if we do it on our own, we wouldn't necessarily be limited to 3 hours a day, and we could add a 4th hour for discussion or something.
Yeah, that might work. Yeah, that's the thing. I have to tell you, clearly I appreciate the AAS helping and everything, but there, as far as I can tell, for our purposes, as this meeting in a meeting, there's no great rocket science going on here that we couldn't do ourselves using Zoom. I think we could pull this off on ourselves, like from a technical perspective. But we could also, by the way, consider actually another possibility, if people are interested, we could actually consider applying for another meeting in a meeting an actual in-person one at the AAS next summer, which I believe is going to be held, I checked, it's going to be held in Anchorage, Alaska. So a nice place for a vacation after the meeting, perhaps. And so clearly we can keep that in mind as another possibility. We can sort of say that this one was really good, but it didn't allow us to have all the discussions and such we wanted. And you know, operations are approaching rapidly and everything. So we might be able to pull one off next summer as well. I have heard that these things are not overwhelmingly competitive, but yes, go ahead.
Neil, I wanted to say from the AA Sustainability Committee, there is news that the next meeting in Alaska, the next summer meeting in Alaska, will probably be the last one in person. All future summer meetings will be then fully virtual.
Oh, okay. Well, okay, that's good to know. I actually had not heard of that. I looked last night at the schedule, and all the other ones out into the future are still listed with cities and everything, but I guess those could be changed.
Yeah, I think it hasn't been announced yet, but I think that's the plan.
Okay, so we may be doing a lot of this stuff in the future then, yeah.
Is that something that had been under discussion before coronavirus, or entirely?
Yeah, so as far as I'm aware, the Sustainability Committee wanted to do something like that long ago, but coronavirus accelerated everything. And so based on the experience from this meeting, I think the consideration is that all the summer meetings will be virtual and all the winter meetings will be hybrid, dual mode.
Oh, okay, that's interesting.
So Neil, it's just something I wanted to add in. If we do stay with virtual meetings, and you know, I think there have been quite a number of positives, obviously missing the in-person interactions, but there are breakout rooms in the normal Zoom.
Yeah.
And if we learned how to manage that, we could actually have people going in and having, you know, 2 or 3 people having a more detailed discussion with each other as you know, issues arose.
Yeah, absolutely. And I will say that, in fact, I've used that in a limited way in my teaching this past semester with those Zoom rooms and everything. So yeah, I certainly think we can pull that off. I mean, Gordon, you're familiar with that stuff too, right?
Yeah, and honestly, I'm not sure. I mean, I'm not sure that the webinar has much added value for what we. I mean, except for, you know, maybe controlling who can talk, but I mean, you know, you have a small.
But for the number of people we have, we don't really need a webinar, I don't believe.
Yeah, that's my feeling.
Yeah. Okay, good. And then just other possibilities, and I'd like to hear if people have any other thoughts on this. Other places where you could have a little meeting of this type focused on this. You know, I know the Aspen Center for Physics has nice summer meetings. They're often pretty long though, but that could be another possibility. And I know the Lorentz Center, I believe in Leiden, right, has you know, facilitates these types of meetings as well. Does anyone have any other possible suggestions that I should keep in mind when thinking about the possibility of a meeting for next summer?
I think the Lorentz Center is quite you need to be at least a year in advance, I think, with them.
Ah, okay. So you really got to have your act together.
Yeah.
Okay.
In Bern, and I think now also with this, with one in somewhere, I think in Beijing, there's the ISSI, the International Space Science Institute, and they facilitate these meetings as well on small and larger scales, and they also provide some funding. However, there may be a restriction on how many people can attend, but you can check out.
Okay, I'll keep that one in mind as well. Okay, well, those are some possibilities for the future. I mean, I do think that we're going to want to be interacting a fair amount as operations are approaching. So, yeah, having some ideas out there are good. Yeah. Okay, so go ahead.
Can I say 2 things? First, the virtual experience was fine. Let me just stress that this is, I think, the correct amount of talks, because from people not in the US, the fact of not being on the same time, it's sometimes you know, a bit more stressing than being there in person, because we would be, you know, on the same time zone. As for the centers, if you decide to do something even outside the US, there is also the Section Center for Astrophysics in the Dolomites, and we can think about that, which is a nice environment, like the Aspen Center for communities like us. Not
can you give me the name again? I didn't catch it. What is it called?
It's called Sexton Center for Astrophysics.
Oh yeah, I know this one.
Yeah,
Yeah, the Sesto thing. Yeah. Okay.
Yeah, exactly. Sesto. Yeah.
Okay. Yeah. Okay. Got it. Yeah, I'll do that one as well. And then I see Aaron Barth is on. Aaron, are you there? I know the Keck, the Keck Institute or whatever. Doesn't Keck have something out in California where you can go for a meeting once in a while?
Oh, that's at Caltech, I believe. So I'm not closely familiar with it, but I've heard of meetings held there.
Or
they have to be space related?
Oh, they have to be space related. And does the National Academies have something out there where you can?
Oh yeah, that's at Irvine. We have on our campus the Beckman Center, which is the West Coast Conference Center for the National Academies, which is an excellent place to have a meeting. It's expensive. But if some funding source was able to support the room rental and meals, it's a very nice place to host a meeting if we could pull it off.
Okay, I got it. So this isn't something where they're charitable and just help you out. This is something where you have to pay.
Yeah, it's because it's not run by the university. It's run as an external business, more or less.
Got it. Okay. Yeah. Good to know. Okay.
The universities are run as external businesses too.
Yeah. Okay, well, I think that's about everything. So thank you again, everybody, for participating, and thank you for all of the invited speakers for giving us a lot of exciting talks and a lot of things to think about. And hopefully we can keep up these discussions regarding metrics and similar, in the coming months on the AGN SC telecons. And let me remind anyone who's on who is not a member of the AGN Science Collaboration that you certainly are welcome to apply. You can just go to the AGN SC webpage and just go to Google and type in AGN Science Collaboration LSST, and it will pop right up. And there's just a little apply button there, and you can apply for associate membership, which is a fairly straightforward thing. Anything else, Gordon? I think we're good then.
I think we're good. We should go to Christy's talk.
Yeah, I think we're at time. Okay, so take care, everyone. Thank you again all for participating.
Thanks, Gordon.
Thanks for organizing.
Thank you.
Thanks for organizing.
Bye, thank you.
Thank you.
Bye.
Thank you. Bye-bye.
Thank you.